Okay, hi. So today we're going to be going over midterm 1 from spring 2022 MA 265. So yeah, let's get started. So in this first problem, we have a system and we're trying to figure out for what value of A is this system inconsistent. And this basically means that there's no solution. So the first thing we can do, and sorry if this is a little blurry, I'll try to make a better setup next time, but we can first write everything out in matrix form. So that gives us A3, 0, 1, -2. And we can perform some row operations on it. And I just like to write out the row operation I'm performing just so it's kind of easy to keep track of. So the first thing we can do is do R2, row 2, subtract A times row 1 from row 2. So we can do that and we get it's the same. And we get 0. A minus 2A is negative A, 3 plus A, and then negative A. And then we can do is add 3 times row 3 to row 2. So we can do R2 equals R2 plus A times R3. And that gives us same thing, 0, 0, 3 minus A now, and then negative A plus 2A, which is A. So at this moment, we can kind of like stop and just kind of consider this row, which is the most important one. So if our system is inconsistent, that means there's no solution. So we would have maybe this row being 0, 0, 0, and then this is some non-zero term. So if we look at our answer choices, if A is equal to 0, right, we would have 0, 0, 3, 0, which would just mean that this variable, z, would be 0. So obviously this would give us a solution, right? So we're looking for this situation. And so if you look at some of the values, right, if A equals 3, we would have 0, 0, 0, 3, which is an inconsistent, we cannot have that. So that would be an inconsistent solution. So that means that when A equals 3, our system is inconsistent. So yeah. So if we go to the next one, we have let A be an m by n matrix, which statement is true. So the first statement we can look at, let me just write out. So m by n matrix, that's m rows and n columns. So okay, so if we look at the first statement, we have ax equals b is consistent for b in the vector space of Rm. And then if that is true, then the rank is going to be equal to the number of columns. So the rank, remember, is the number of non-zero rows, so we should keep that in mind. And the consistent, again, means that there is a solution for all values b. So one way to think about this is we can come up with some examples and see if it matches with what the statement says. So one that comes to mind is this case. So in this case, m equals 2, and then n equals 3, because there's 3 columns and 2 rows. So this is going to be our A, and then we do it times x, so x1, x2, x3 equals some b1, b2. And I'm just writing out like the individual terms here, so it's kind of easier to see. So this is a consistent equation for all b in the vector space r to the 2, because as you can see, if you multiply out this matrix, you're gonna get x1, x2. So you can set x1, x2 to be any values you want, and that could be equal to b1, b2. So that covers everything in the R2 vector space. But if you notice here that the number of non-zero rows, or the rank, is actually 2. So that's not equal to the n equals 3, so we can say that number 1 is not true. Okay, so I'm going to explain 2 again because I don't think I did a very good job the first time. So if the equation ax equals 0 has only trivial solutions, so that means that the only solution to that equation is when x is equal to 0, then the rank is equal to the number of columns. So if we have that case, right, what we have is essentially when we row reduce, we have that, for example, for a 3 by 3 matrix, we would have 0, 1, 0, 0, 0, 1. So all of these pivot entries would correspond to a 0, and all of these columns would be filled. So it wouldn't matter if we had, say another row of zeros here. This means that every possible variable here corresponds to 0. So in the case of the first part, right, this is not a valid a for ax equals 0 having a trivial solution, because if you recall, we can have, this becomes x1, x2, right? So we can have any value for x3 and it really wouldn't affect the result. So that means that there's this free parameter, which is x3, that allows us to have infinitely many solutions. So in the case when there's only a trivial solution, every single variable, so like x1, x2, and x3 must be occupied, must be equal to 0. So that corresponds to these pivot entries being equal to 0. So because of that, the rank has to be equal to the number of columns, because every single variable, such as these x1, x2, and x3s, must be equal to 0. So that corresponds to these pivot entries, and thus the rank would be equal to the number of columns, which is n. So hopefully that kind of makes sense. If not, let me know so I can work on explaining it better. So this is correct. Okay, so for number 3, we have if the rank of A is equal to n, then the rows of A form a linearly dependent set. So again, you can come up with examples for this situation. So obviously, there's different examples that actually do satisfy this equation. So for example, something like 1, 0, 0, 1, 1, 1 does work, is that you can see that the rank would be equal to 2. And remember, the rank is the number of non-zero rows in the row reduced echelon form. So this one would have rank 2, and the rows do form a linearly dependent set. But something that comes to mind is this matrix. So we can see that this is in the row reduced echelon form, so the rank is equal to n, which is in this case 3. What happened there? And so the rows in this case do not form a linearly dependent set. In fact, these are linearly independent. So that's an example in which this statement is not satisfied. So this is false. For number 4, we have rank. If the rank is equal to n, A is a square matrix and A is invertible. This is true based on just the definition of something being invertible. So we see that this is true. If the rank of A is equal to m, the linear transform is 1 to 1, then A is invertible. So this is true especially because of this phrasing here that it's 1 to 1. So this means that for every x is getting mapped to some other matrix. And so that means that an inverse exists for A, because you can then consequently map back from this AX vector, or matrix, So in this sense, if an inverse exists, then A is invertible by definition. So your answer is going to be D. In this problem, we're talking about linear transformations. And so, so essentially we're transforming from this vector space with dimension n to the vector space with dimension m. And so we can look at these statements and figure out which one is not necessarily true. So for the first one, also, a key point to this is the fact that this transformation is 1 to 1 and it's linear. So for the first thing, for part A, we see that if v1 and v2 are linearly independent, so are t v1 and t v2. So this makes sense, right? That linear independence is preserved across a transformation, because across specifically a 1-to-1 linear transformation, because you're mapping. You can imagine that you're mapping each vector to its own vector in this new vector space. And because of that, linear independence will be preserved, because you're only doing a matrix multiplication against each vector. So this one would make sense. If TV equals 0, then V is equal to 0. Again, this makes sense because of our 1-to-1 linear transformation. So if we're doing A times V, right, equals 0, we're only mapping one vector to this 0 vector. So if A was actually equal to 0, right, 0 times V, that means we're mapping multiple vectors. So like we could be mapping like 1, 0, 1, 1. It doesn't really matter because it would all get mapped to that same 0 value. So in this case, V must be equal to 0 because otherwise it would not be a one-to-one transformation. So this is not true. So m must be greater than or equal to n. So this kind of makes sense if you kind of think about it in terms of geometry. So if we're going from like the R2 space to the R3 space, right, there's enough points, there's more points in R3 than there are in R2, right, because of this added dimension. So, you can imagine that you're extrapolating all these points or vectors in a plane to some 3D space. Versus if you were trying to go the other way around, that means you'd have to kind of compress this down and condense different vectors to a single point on this plane. So in this case, yeah, m does have to be greater than or equal to n to ensure that this one-to-one transformation is maintained. This is true. So d t of v plus w is equal to t of v plus t of w. So this is simply a linearity property, right? Because this is a linear transformation. So since the transformation is essentially a times v plus w, equals, we're just multiplying this out, right? We're just multiplying this out. What's the word? Distributed property. So you get av plus aw, and this is just a transformation of v, and this is a transformation on the w vector. So based on linearity properties, we are able to get this equation. So this is true. So obviously by elimination, this is correct, or this is not always true. But you can also kind of come up with this if you think about some counterexamples. So one that like comes to mind is if you go from R2 to R3, right? So our A matrix could be 1, 0, 0, 1, 0, 0 times x1, x2, and then equal to some vector. So when would this equation not have a solution for ax equals b? So we're trying to figure out like what b maybe wouldn't work for this. So notice that if we multiply this out, we get x1, x2, and then 0. So if we have this be something like 1, 1, or 2, this is just a non-zero term, then this is inconsistent because we would have 0, 0, 2 as this bottom row, right? So in this case, the equation would be inconsistent, so we might not necessarily have consistency for all b in r to the 3. So this is the incorrect one. Alright, so in this problem we have which of the statements were true. So for statement 1, we have if this R2 to R2 is a linear transformation with the matrix A, and we have this information about A transpose times A as being the identity matrix, then for any parallelogram S, the area is equal to the area of the transformation. So recall that the area of a parallelogram is equal to the determinant of S, where S has columns being that describe the sides of the parallelogram. So we have the determinant of S, and we're trying to see if this is equal to determinant of A absolute value times the determinant of S. So when we have this piece of information about A transpose, we have that A transpose times A is equal to I. We can take the determinant of this, of both sides. So remember, we can apply some rules about determinants. So if we have AT times A and we want to find the determinant of it, you can split it up into the determinant of the transpose of A times the determinant of A. And this is equal to 1 on the right-hand side because the determinant of the identity matrix is 1. So this, we can also apply the property that the transpose of A is equal to, the determinant of the transpose of A is equal to the determinant of A. This means that determinant of A squared equals 1. So the determinant of a is going to be absolute valued. So either way, the magnitude of the determinant is going to be 1. So this means that this is going to be 1 no matter what. So that means that it is equal to the determinant of s. So this statement is true. Now for statement 2, we have that the homogeneous system, which means that we have something like ax equals 0, which is a system of n equations and n variables. So this information tells us that this A will be, that this will be an n by n matrix. And it has infinitely many solutions if and only if the determinant of the coefficient matrix is 0. So because this is a square matrix that we're dealing with, essentially A will be a square matrix, we have the property that if the determinant is non-zero and it's a square matrix, that the coefficient matrix is invertible. And if an invertible matrix exists, then you will have a unique solution for every variable, which means that you will not have infinitely many solutions. So thus, if the determinant is non-zero, if the determinant of the coefficient matrix A is 0, then you will have infinitely many solutions because this is a homogeneous system of equations, so you won't get anything that has a no solution, such as 0, 0, 2, because everything on this side would have to be a 0. So this statement is true. And then for 3, we have A is a n by n matrix with non-zero determinant. So based on the definition of invertible, this part of the statement is true. And the inverse of A is given by this. So because we know that this is an invertible matrix, we know that an inverse exists. So we can write it as A inverse times A is equal to 1, or equal to the identity matrix. This means we can take a determinant of both sides. So we have a determinant of A inverse times the determinant of A equals to 1, based on this determinant properties. And so solving for this determinant of inverse of A, we get determinant of inverse A equals 1 over the determinant of A. We can compare this now by taking the determinant of this expression they give us. And when we do that, we have the determinant of the A inverse equals, so this is going to be a scalar multiplied by A. So this means, again, based on the determinant properties, we have the determinant of A, or C times A, where C is a scalar. We have C to the n times the determinant of A, where n is just a side length of A. So in this case, we have 1 over the determinant of A to the n times the determinant of A. And as you can see, these two expressions are not equal. And so this statement is false, even though this part of the statement is true. So for part 4, we have this linear transformation where we're taking some parallelepiped S and it transforms to a flat parallelogram. So then the determinant of A must be equal to 0. So one way of thinking about this is that the volume of the parallelepiped is equal to the determinant of S. And so when you apply a transformation, then the volume is going to be equal to the determinant of S times the determinant of A. And so if this becomes a flat parallelogram, then the volume would be equal to 0. And for that to happen, then the determinant of A must be equal to 0 since it originally had volume as a parallelepiped. So this is the only way that the transformation can yield a flat parallelogram. So this is true. So now we have 1, 2, and 4 being true, so that gives us the answer choice C. So this problem is asking us to see which collection of vectors are linearly independent. So right off the bat, we can see that this one is not linearly independent because this is a constant multiple of this vector. Similar thing with this one, that the 0 vector can be written as a linear combination of any vectors as long as the coefficients are 0. So that means any set with a 0 vector is not linearly independent. So the thing with these two vectors is that you can see that there are more vectors than there are non-zero terms. So if we look at this case, we see that this row is 0, but these two non-zero terms, we see that the basis for these vectors would be something like 1, 0, 0, 0, 1, 0, and then 0, 0, 0. And this is actually what you'd get if you row reduce this, because there are more vectors in non-zero terms. So they will not be linearly independent, because you would be able to write this third term, for example, as a linear combination of these two vectors. So the same reasoning applies here. So these two are both linearly dependent, and that leaves A as being linearly independent. And you can verify this through row reduction. So if you actually go through and row reduce, you should get something like this identity matrix, which means that the only solution to these vectors, so basically, if you were to set this equal to some x times 0 equals 0, the only solution would be that x has to be 0, which means that they're linearly independent. So that's for 5. And for 6, we can use some determinant properties. And first of all, we know that if we add non-zero scalar multiples of one row to another row, then the determinant is the same. So because of that, we can kind of neglect these terms because we're just adding rows, scalar multiples of rows. So we have then, because of that, we have 3a, 3d, 3g, 2c, 2f, 2i, b, e, and h, another determinant. So this equals, okay, let's say the determinant of b is this. So this remains the same as the determinant of b. And then the other thing we can do is take the transpose. And so if we take the transpose, the determinant remains the same. So we can take the transpose and we get 3a, 3d, 3g, 2c, 2f, 2i, b, e, h, the same as before. And now we're going to swap some rows. We want essentially, the overall goal is to get this B matrix to look like the A matrix. So what we can do is we can swap these two rows, columns, excuse me. And when we do that, we get a negative determinant. So this becomes 3a, 3d, 3g, b, e, h, 2c, 2f, 2i. That equals a negative determinant of b. And then what we can do is realize that these multiples, we can take them out because we can take them out of the determinant, right, based on our properties, because this is just only being applied to, for example, one column. So if we do that for both of these, we get A, B, C, D, F, G, H, I equals negative 1/2 times 1/3 times determinant of B. Oh, I think I'm missing oh, never mind. Sorry, we're good. So anyways, this now is equal to determinant of A, right? So this is determinant A, which is -2. So then we can solve for the determinant of B, and we get determinant of B equals -2 times -2 times 3, which is 12. So that is B. So our next problem is about vector coordinates. So essentially what we have is that this is our coordinate system. So you can think of it as like, instead of, with your normal coordinate system, this is in R3, but just imagine, that this is your normal coordinate system and we're just making it some different coordinate system. So in this problem, V1, V2, V3 is the coordinate system for this basis B. So H is the span of these. So first we can determine if X is in H. And so one way to do this is to do row reduction. So you could do 3, 2, 1, 2, 0, 3, 4, 1, -1, 1, -3, 2, and then 9, -8, -1, -5. And then I trust that you can row reduce this. And once you do that, you can get 1, 0, 0, 2, 0, 1, 0, -3, and 0, 0, 1, -3. So this means that the solutions, the linear combination of v1, v2, v3, and to make x exist because we have a solution for the linear combination constants. So because of that, we can confirm that yes, it is in H, and so consequently, this is the b-coordinate vector of H, of x. And you can actually check this by noting that, right, these are the constants that form a linear combination. So we would have 2v1 minus 3v2 minus 3v3 equals x. And we can check if this is correct. So that's one way to check your work with these kinds of problems. And so if you do this check, you will find that it is the same. So the b-coordinate vector, or the coordinates of x in this basis is 2, -3, -3. So our answer is B. So in this problem, we have a linear transformation, which is described with these three vectors. So first, we're asked to find the standard matrix of T. Recall the standard matrix of T is essentially the columns are the transformations of a linear basis. And the linear basis essentially being this 1, 0, 0, 0, 1, 0, and 0, 0, 1 vectors. So this is kind of convenient because it's given to us already in the transformations we are given are in terms of the linear basis already. So from that, we can just see that A is equal to 1, 0, 5, which is the transformation of the linear basis with the pivot column being the topmost entry. Not pivot column, pivot entry being the topmost entry. Then we have 2, 1, 6, and then 3, 4, 0, which just corresponds to this 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that is the standard matrix of T. Now we're asked to find the image of the vector in part B. So that means that we're trying to apply this transformation to the vector u. So we have A times u, which is the transformation on u, which is equal to 1, 2, 3, 0, 1, 4, 5, 6, 0 times 1, 2, -1. And that gives us, basically once you do multiplication, you get 2, -2, and 17. So this is the transformed vector u. In part 3 we have is the vector b in the range of T. So when it's asking for the range of T, it's asking if it's in the column space of T. So one way you can do that is to see if a valid solution exists for T of x equals b. So we can have 1, 2, 3, 0, 1, 4, 5, 6, 0, and this is just the A matrix times sum x equals b, which is 10, 6, 27. And what you can do is you can just do row reduction. So you have 1, 2, 3, 4, 5, 6, 0, 10, 6, 27. I'll just write out one of the steps of the row reduction process, but I trust that maybe you can try this out on your own and hopefully get the same result. So then this comes out, and then we end up with 1, 0, 0, 0 in the row reduced echelon form, 3, 2, 1. So this means that our x, right, this is x1, x2, x3. So it means our x1 is equal to 3, x2 is equal to 2, and x3 equals 1, which means that our x vector is 3, 2, 1. And because this solution exists, it is in the range of T, and x is equal to this vector right here. Okay, so in this problem we have this matrix A, and we want to have it in reduced row echelon form. So what that means is we want to have something in the form where the leftmost entry on any row would be 1, and that 1 would essentially be the pivot entry. And within the column holding that pivot entry, all the other entries you want to be 0. And additionally, we want to have any 0 rows be at the bottom, and then we also want each pivot entry to be in a column that's to the right of the initial pivot entry. And that'll make sense once we row reduce this. So the first thing we can do is we can do row 2 equals row 2 plus 2 times r1. So I'm just adding 2 times row 1 to row 2, and that gives me 1, 4, 0, 1, -4, 0, 6, 0, 2, -8, 1, and 9. I can further reduce this by doing R3, by subtracting 2 times row 2 from R3, and that gets me the same thing on the first 2 rows. And then we have 0, 0, 0, 1, -3. So be careful because we're not actually in row reduced echelon form yet, because even though we have these pivot entries being to the right of one another as you go down the rows, every pivot entry, the column that the pivot entry is in must have all 0 terms except for the pivot entry. So that's not the case in this column. So we need to go one step further, and we can do that by just having subtracting row 3 from row 1. That gives us 1, 0, -5, 0, 7, 0, 1, -4, 0, 6, 0, 0, 0, 1, -3. So this is the row reduced echelon form of the matrix A, and it satisfies all the requirements. So now we're asked to find a basis for the null space of A. So the basis for the null space of A is essentially the vectors that span the solution set for AX equals 0. So looking at A, we have in the row reduced form 1, 0, -5, 0, 7. Let's rewrite it here. And this would be equal to 0. So what we now know is that x, right, in this case, if we just wanted to write it maybe something like this instead, that'd be clearer. x1, x2, x3, x4, x5 equals a 0 vector. So what you can imagine is that each of these columns, right, corresponds to the variables x1, x2, x3, x4, x5. And so when we have what we previously had, I'm going to write that one now. 0, 0, 0. Right, we see that we have some free parameters, and so our free variables in this case would be x3 and x5, and we can write x1, x2, and x4 in terms of those variables. So I will do that now here. Right, we can write the solution set as some linear combination of x3 and x5. So from x1 from x1 we can move these 2 terms to the other side, and that gives us 5x3 minus 7x5. Then for x2, move these to the other side, we get 4x3 minus 6x5. And then x3 is just x3, right? So we just leave it at that. And x4 is equal to 3x5. And x5 is just x5. And then what we can do is we can split this into the respective x3 and x5 vectors. And what I want to do is just going to parameterize. I'm going to call this variable parameterized by t, and this one parameterized by s. So replacing the x3s with t's and the x5s with s, we get 5, 4, 1, 0, 0 times t plus -7, -6, 0, 3, 1 times s. This is the solution set for the null space of A, and thus the basis for the null space will be these 2 vectors, which means that the basis is 5, 4, 1, 0, 0, and -7, 6, -6, 0, 3, and 1. And you can verify these are linearly independent, obviously, by comparing the 0 entries. So in this last part, we're trying to find a basis for the column space of A. So that's the span of the columns of A. we want to figure out which vectors span the columns of A. So obviously one way to do this is to check for linear independence among these columns. And so, just from looking at the A vector, we can see that you can pick any vectors that are linearly independent, but right off the bat, you can kind of see that these three are linearly independent. So obviously, if you compare the 0 positions, you can see that these three will form a linearly independent set. And another way of looking at this is looking at the row-reduced echelon form of A. So you can see that you have the 1, 0, 0, 0, 1, 0, and 0, 0, 1 columns, and these are clearly linearly independent columns that describe the columns of A. So your answer could be Your answer could be, for example, 1, -2, 0, 0, 1, 2, and 1, -2, 1. That is one basis that works for A, and another basis that works is 1, 0, 0, 0, 1, 0, 0, 0, 1. So any of these two answers would work because this spans the columns of A. And you can check this yourself. Just check that they do span. That the columns of A can be written as a linear combination of these bases. So in this last problem, we're asked to find the determinant of A. So what we can do is do cofactor expansion across this row. I'll pick this row just for convenience, but you can pick whatever you want. So first we have 0. So this is starting off in the corner, which means that the coefficient in front is a positive. So even though it doesn't really matter because it's 0, but you're going to eliminate the column and row that this entry is in. So we have 0, 3, -3, 8, and that is the resulting determinant that you're going to multiply this entry by. And then for the next one, we have -1. So when we remove this one, this row and column, we have 1, 3, 4, 8. And then when we have the last entry here, we have 1, 0, 4, and -3. So this becomes 0, and then we have -1 times 8 minus 12 plus 2 times -3, which gives us 4 minus 6, which is -2. That's the determinant of A. And now we're asked to find a determinant of 2A and a determinant of the inverse of 2A. So recall that the determinant of some scalar times some matrix A is equal to C to the n, which C is a scalar, times A, where n is essentially if you have for this n by n matrix, it is the number of columns or number of rows. So we also have, if A is an invertible matrix, then the determinant of inverse of A is just determinant of the inverse of A is just 1 over the determinant of A. So this gives us the determinant of 2A being 2 to the 3. So that's 3 because A is a 3 by 3 matrix. So that is multiplied by the determinant of A, which we just figured out was -2, which gives us -16 as a determinant of 2A. Then the determinant of 2A inverse is 1 over the determinant of 2A, which is -1 over 16. Okay, so then our final problem we're trying to find the 2, 3 entry of matrix B, where B is the inverse of A. So recall that from Cramer's rule, you can figure out that the inverse matrix, which is shown here, is just A -1. The ith row and jth column, the entry at that location, will be equal to 1 over the determinant of A times -1 to the I plus j times the determinant of A ji. This matrix is important to remember. So this is the matrix that you get when you delete the jth row and ith column. So we'll be able to see that more clearly, but applying that here, you have that B, the 2, 3 entry of B, which is the second row, third column, corresponds to 1 over the determinant of A times -1 to the 2 plus 3 times the determinant of A once you remove the jth row and ith column. In this case, that would be the third row and second column. So this looks like, so A originally is 0, 1, 2, 1, 0, 3, 4, -3, 8. And we're getting rid of the third row and second column. We're left with 0, 2, 1, 3. This gives us, so we know that the determinant of A is -2 from before, times -1 times the determinant of 0, 2, 1, 3. This gives us 1 over 2 times -2, which is -1. So that's the entry at the second row and third column of matrix B. So yeah, that was it. Hopefully that made sense. If something doesn't seem right, please let me know. And yeah, good luck.